Hello, welcome to the Engineering Circuit Analysis Tutor. We're talking about three-phase circuits. In this lesson, we're talking about the delta load line current to phase current conversion. So it's a big sounding title, but basically what we want to do is we want to learn how to work with delta loads. Now, let me give you a little bit of a backstory here in the beginning of this batch of lessons to give you the roadmap of where we're going and where we've been, and kind of tell you what we're doing so when we dig into it, you won't lose the big picture. In the last 20 some odd lessons in the previous volume here, we've done the three-phase circuit analysis, what I called part one. Effectively, that was all dealing with what we call YY circuit analysis in the three-phase configuration, YY circuits. If you haven't watched that material or if it's been a long time, I strongly recommend, in fact, I insist that you go back and watch those. Even if you already know what a YY circuit is, because I introduced a lot of terminology and spent a lot of time teaching you a lot of fundamental things that if you don't know that stuff, this stuff is just going to seem hard, and it's not hard. It's very simple stuff. But you have to have that bedrock, okay? So here what we're going to do, in the previous few sections, in previous 20-something sections, we've done Y source and Y load, Y configured source, Y configured load. Now, the only thing we're going to do here in the beginning is change one part of this, and that's we're going to look at a delta load instead of a Y load. Now, the big picture is ultimately what we're going to end up doing is we're going to develop some relationships that deal with the delta configuration and converting between the phase current and the line current and so on in a similar way that we have done in the Y configuration. So, and we're also going to learn how to take those delta loads and kind of convert them to a Y load in order to make a single phase equivalent circuit. So the big overarching picture is in a lot of cases what we're going to do is take that delta load, which looks different than in the previous cases with the Y loads, but we're going to end up modeling them as a Y load so that we can write a single phase equivalent circuit like we've been doing before and calculate some of the fundamental quantities. All right, so all of that YY analysis was crucial not only for the YY circuits, but for the Y delta circuits too, because we're going to end up modeling a lot of those loads as a Y load anyway. Then later down the road, we'll look at delta sources and all the different configurations, and we'll look at power calculations. Now, in this lesson, what I'm going to do is I'm going to give you the punchline of the difference between Y and delta loads, and I'm going to give you the conversion relation without deriving it. And we're going to get into all of that, just like we had to convert line voltage and phase voltage before. We're going to have a similar relation for the line current and the phase current in the delta load. And I'm going to kind of go through a lot of it with a lot of talking, a lot of comparing and contrasting to kind of get it all out, everything that I think I have in my brain. I'll try to get it out for you. It'll be a little bit all over the map, but I'll get all of the relations out for you. But I'm not going to derive it in this lesson. In the next lesson, it's going to be almost exactly the same as what we're talking about here, except I'll tabulate it for you so it's a little easier for you to remember the actual results. So I'll do a little more talking in this lesson, and I'll do less talking in the next lesson with the important points kind of tabulated for you. And then in the lesson number 3, what I'm going to do is derive the relation. So I'm saving the derivation for the end because I want to get the punchline out for you so that you can easily see how it compares to YY circuits. Because ultimately the punchline is what you're going to use in your circuit analysis. But we will get to the derivation of it, so don't stress out too much about that. We are going to derive it. Okay. So enough talking, let's look. So we have a Y load. So don't forget, here's our 3 lines, A, B, and C. Over there are the lines and the sources. Here we just have the load A, B, and C. And notice that we have a phase to neutral, or I should say a line to neutral voltage VAN, and we have a line to line voltage VAB. We're going to talk about that in just a second because ultimately you want to compare and contrast what you know from before to what we're learning new now. And I am going to talk a lot more about that configuration as a review, but just to again show you where we're going, this is the delta connected load. Again, you have 3 lines, same as before, because you have 3 transmission lines, right? It's just that the load is not connected in that Y arrangement. You have it arranged like a triangle, right? And so you have some currents going through each leg of the triangle. We have them labeled. We'll get into all of this stuff later, but you have the same line current coming in, AA, little b, big B, little c, capital C, because these are the capital letters at the load, and you have the lowercase letters on the other side of the line. But as the currents come in, because it's in a triangle, they split here, and so you have this kind of arrangement going here. We're going to talk about this in just a second, but before we get to that, I just wanted to kind of show you where we're going. We're going to start talking about what you already know. So a lot of this is review, but it is critical review. It's stuff that I wouldn't mention again if I didn't think it was important. I'm trying to draw some connections. So let's talk about the Y-connected load. A lot of this stuff should sound familiar. What are the important points? So I'll put some asterisks here. We'll talk about the important points of a Y-connected load. We have the line current here, and then we have each phase, for instance, phase A, phase B, phase C. But the line current going through the line actually goes right into the phase and goes right through each of the phase, each of the loads of the phase. So what we say is that the line current in this configuration is equal to the phase current. Because remember, when we use the term phase current, we're just saying it's the current going through each phase of the load. And since this is the line, it's directly connected to the load, the line current is actually equal to the phase current in this configuration. And because they are the same, in the Y-connected configuration, we have no conversion required between the two because they're the same thing. So no conversion needed. And what I mean by that is in a Y-connected load, if you know the line current, you already know the phase current. You don't need to convert between them. They're the same thing. You can see it from the drawing. All right, let me switch colors. And we go on to kind of important point number 2 for the Y-connected load. The reason I'm writing this stuff down is I'm going to compare and contrast it to the delta load in a second. So this is what we spent most of the last course on. You have something called a line voltage, which is between the lines, A and B, and you have a phase voltage, which is the voltage across the phase. But you can see from the diagram that the voltage across this ZA here, this voltage here, is what we will call VAN, that's the phase voltage. It can't be the same as the line voltage because obviously they're taken between two different points. So in this configuration, the line voltage, which just to refresh your memory is VAB, is not equal to the phase voltage, which, just to refresh your memory, is VAN. Okay, because the line voltage is not the same as the phase voltage, that is what drove our need to develop a conversion relation between them. So we need conversion equation. In a nutshell, this is really the core of what we did in the last lesson. The equation that we use to convert between the line voltage and the phase voltage, I'm going to write it down again just to make sure everybody's on the same page. But ultimately, the thing I want you to realize is that you only need a conversion equation between the line voltage and the phase voltage because this configuration dictates that these voltages are different. That's why you need a conversion equation, because it's often useful to have one, because they're different, right? But for the currents in this configuration, the line current, the phase current, you don't need any kind of conversion relation, not because we forgot to derive it, but just because they're the same thing, so you don't need it. So let me go and write down what I know that you already know, which is that conversion relation between line voltage and phase voltage in a Y-connected load. And the way that you should think about it in your head, right? Mentally, you should always have with engineering and any kind of math, really, it's bad just to memorize equations because you don't know what you're doing. So when I teach, I'm trying to tell you how to think about the equation. What is it saying to you? So I can write the math out, and I will do that, but I want you to have an idea of what it means. And so in this case, the line voltage, which is between VAB, between the two lines, is equal to the square root of 3 times the phase voltage. I'm going to say PH here, voltage. Right? But we also have to phase shift the result by either plus or minus 30 degrees. Remember we had that plus or minus? And that plus or minus is basically, if it's a positive phase sequence problem, you choose the positive sign, and if it's a negative phase sequence problem, you choose a negative sign. But the way, that's kind of in the weeds. What I really want you to know is the line voltage, which is the AB, is equal to square root of 3 times this phase voltage. And then you have a phase shift also of 30 degrees, but whether you add or subtract 30 just depends on the phase sequence of the problem. The reason I'm going through all this stuff again is because this equation for the delta load is going to look really similar. It's not going to be exactly the same, but it's going to look really similar. So knowing the overall form and remembering the overall form of this equation is going to help you remember the other one. And it's going to tie in nicely. So that's why we're doing that. So this is how you write it in terms of words, but you usually don't see equations written in terms of words in your textbook. What you're going to see is something like this. You're going to see VAB is equal to the square root of 3 times, for phase A, it's going to be VAN, which is the phase voltage, VAN. You might see that written as V phi, the phase voltage, whatever phase you're talking about. In this case, I'm writing the equation for phase A. That's why everybody has A in there. So this is the line voltage, this is the phase voltage, just like we have written up here. And then you have angle plus or minus 30 degrees. So this is what you would see in your textbook. You might probably see it with the V phi in there. That just means the phase voltage of whatever phase you're talking about. All right. So the way you remember this guy is, for the sign, you say, you choose positive for ABC sequence. That's the positive phase sequence. And you choose the bottom sign for the ACB, which is the negative phase sequence. And we've been doing that over and over again for our problems. Now, things can get a little confusing if you don't have practice or kind of know to look out for it when you go the other direction, right? Any equation can be solved for the other variable. So if I'm trying to find VAB and I already know this, it's very simple. I just take this times this. If it's positive phase sequence, add 30 degrees to the phase, and I'm done. I've calculated this. But in many cases, I have to go backwards the other way. So let's go and do that and just write that down. This is not a new equation. It's just simply taking this one and going the other direction. So I'll say to go other way. In other words, what if I want to find VAN, right? The way you do that is you say VAN, you just literally solve the equation, right? It's VAB divided by the square root of 3, right? And then you have to divide by this phase. So you have, there's an implied 1 here as the magnitude of this phasor, so I'm going to write it as 1 at an angle plus minus 30. Right? So that's how you would do it in your calculator. If you really wanted to find out what this is, you would take VAB, you would divide by square root of 3, and you divide by either plus 30 degrees or minus 30 degrees if it were an ABC sequence. But don't forget, one thing I taught you in the last set of lessons, I actually went aside and taught you this, is when you divide by a phasor, let's pretend you have a positive phase sequence, so it's actually positive 30 degrees you're dividing by. Then let me go and write it out and you'll see what happens. What you end up doing when you really write it, and you'll see this in some books, is why I'm going through it here. For a positive phase sequence, we've chosen the top sign of plus 30 degrees. That means that VAN is going to equal to VAB. Whoops. Let's do it like this. It's going to be 1 over the square root of 3 times VAB, and I'm dividing by plus 30 degrees. Whenever I divide by plus 30 as a phasor, what actually ends up happening is I end up changing that division to a multiplication by negative 30 degrees. Okay? So if that seems confusing to you, if you don't know why I've changed the sign from plus to minus for this positive phase sequence, then you need to go back probably in my previous lessons and look at that. But the bottom line, punchline, is because this phasor is an exponential on the bottom. It's e to the j30 on the bottom. So it's e to the j30, and when I move them upstairs, the sign of the exponent changes, you know, just like any exponent. It's like 1 over x squared is x to the negative 2. You move it upstairs and you change the sign of the exponent. So if I move this upstairs, which is what I've done here, I change the sign of the exponent. So for a positive phase sequence, if I'm going backwards, you divide by square root of 3, you have your line voltage, divide by square root of 3, and you shift like this, negative 30 degrees because of this. And then let's go ahead and switch to a different color. If it's a negative phase sequence, then it's going to be the same sort of calculation. It's going to be VAN is 1 over square root of 3 times VAB. What do you think it's going to be? In that case, if it was negative, I would have chosen the bottom sign. Then if I move them upstairs, it's actually going to be a positive 30 shift like this. These should always be opposites of one another. So that concludes our summary of almost everything we did in the last class. Basically, we have a Y-connected load. Well, the main points is that the line current is equal to the phase current, so we don't ever have to convert between them. But the line voltage, line-to-line voltage, is different than the line to neutral voltage, which we also call the phase voltage. So we need a conversion equation. The general form of the conversion equation is that the line voltage is the square root of 3 times the phase voltage plus minus 30 degrees, where we choose the sign of that based on the phase sequence. So you just use it like this almost all the time, but if you do have to go the other way, you don't need to memorize another equation. You just start with the one we have and you manipulate it to do whatever you're trying to do. So if you're trying to find this guy, you just divide by square root of 3, divide by the phase, but you just need to remember that when you divide by the phase, you move them back upstairs, it's like multiplying by the opposite sign here, multiplying by the opposite sign. And we've done lots of problems to show you all of that in the previous sections, in the previous lessons. That's why I wanted to bring it up to you. Okay, so let's keep that in our mind, that this is how it goes. Line voltage is square root of 3 times phase voltage, phase shifted plus or minus 30 degrees, where we choose the sign appropriately. Now we're going to go in and we're going to write similar relations for the delta load and kind of draw some parallels with the Y load, right? We're not deriving them. I'm not deriving them now. I will derive them later. But I just want to get it out so you can compare and contrast them in your head. All right. The main thing to understand about this, we'll put some asterisks here. Okay, first of all, there's no neutral connection at all. That's one difference between a delta load and a Y load. If you go back to the Y load, we labeled this. I didn't actually label it here. This is the neutral connection. And we've talked about when it's a balanced YY, we can take the neutral conductor out. But still, you have a common point here. We call it the neutral connection. But which is a common point connection. In a delta load, there is no neutral connection because there is no common point. So that's just something you have to get used to. If you talk about the neutral in a delta load, it just doesn't make sense. It's not there. Okay? So I'm not going to write that down, but just know that there's no neutral connection. Okay? So there's no VAN, for instance. VAN, meaning this voltage here. VAN. There is no VAN in this circuit over here because there is no N. There's no neutral. Okay? So what do we have then? First of all, let's go over here and talk about the voltages, okay? So in this case, we said the line voltage is not the same as the phase voltage. But here, what is the line-to-line voltage, VAB? That's the voltage from this line to this line. But because of the way it's drawn, you see this is the A phase, this is the B phase, and this is the C phase. So if this is the A phase, the voltage across this load here is exactly the same as it is across the line. So because of the way this is, look, you can just see it very easily for the A phase. The voltage across the line to line, is the same as the phase voltage because the phase voltage is defined to be whatever voltage falls across each phase, right? So the point that you need to understand is VAB, VBC, and VCA they're what we call the phase voltages. Right? And in this case, the phase voltage is equal to the line voltage. And because they are the same, phase voltage and line voltage in this case, VAB, basically the same thing, no conversion is needed. Now, before we go on, let's go and compare that to the other case. The phase voltage and the line voltage is exactly what we needed to convert between in the other case. So you see, these are kind of like peanut butter and jelly circuits. In this case, in the old case, the case we've been doing forever and ever and ever, we always had to convert between the line voltage and the phase voltage because they were different. But in the delta load, because of the different way in which it's connected, the phase voltage is the same as the line voltage, so we never need to convert between them. If we know the line voltage, we know the phase voltage. If we know the phase voltage, we know the line voltage. You can look for any one of these. Let's look at the C phase. The phase voltage for the C phase is this because it's the voltage across the phase. But that's exactly the same as the voltage between A and C because the line is connected to each side of that load. So the phase voltage and the line voltage is exactly the same for this delta connection. That's very important for you to know. So you're never converting with the square root of 3 or anything between line and phase voltage in a delta load. You already know what it is. Once you find one, you know the other. Okay? But let's look at the current. This is what we call a line current coming from little a, big A. This is the line current. But when it gets here, look what happens. It splits. So the phase current, which is the current through the A phase, is different than this line current through the A phase. So the line current for this connection type, the delta load, is not the same as the phase current. And because of that, we need a conversion. But the crucial thing for you to know is that in the delta load, you need a conversion equation, but you're not converting between voltages. Those are the same, right? You're converting between currents. You're not converting between the voltages because those are the same. You're converting between the current. Specifically, you're going to have an equation that's going to convert between the line current and the phase current. And guess what? It's going to look really similar to the other equation we've always been using. It's going to have a square root of 3, and it's going to have a phase angle involved in it. So let me make sure I did not skip any steps. So the peanut butter and jelly duality of these guys is that line voltage not equal to phase voltage for this type of circuit. Line voltage, or phase voltage, is equal to line voltage in this circuit. In this circuit, line current is equal to phase current. In this circuit, line current is not equal to phase current, so we need a conversion relation. Now let's go one step further. The type of conversion equation that we've used for the voltage in the previous circuit, in the Y circuit, is like this. Line voltage, square root of 3, phase voltage, phase shift. Now you see why I wrote that stuff out, because it's going to look basically the same. What we convert between in the delta load is going to be something like this. The line current is equal to the phase current. Whoops, I forgot one important thing. I bet you know what it is already. Let me just get rid of this. Is equal to the square root of 3 times the phase, I'll just do it like this, current. Right? Everything is the same so far. It's line current, square root of 3, phase current. Now we have a phase shift. Now here's where it gets a little different. It's still 30 degrees, but it's minus plus. Not plus minus, it's minus plus. That's not a typo. 30 degrees. But it's exactly the same sort of thing. What we choose is, we choose the top sign for the ABC positive sequence, and we choose the bottom sign for the ACB, which is the negative phase sequence. Let that sink in for a second, because ultimately this equation is going to absorb your time for the next, I don't know, 7 or 8 lessons, because we're going to solve a lot of problems with delta loads. But from a form point of view, it's kind of beautiful in a weird way. They're the same thing. Look at this equation. Line voltage, square root of 3, phase voltage, phase shift. Now in the other load, still a line quantity, line current though, square root of 3, phase quantity, phase current in this case, everything's the same, and a phase shift. So the only thing you have to remember is that in the delta load you're converting between currents, but it's the same form of the equation. And the phase shift is flipped around, so for a positive sequence you have a negative sign here, and for a negative sequence you have a positive sign here. So really, this equation in this form is what you really have to remember to solve almost all of these delta load problems, at least in the beginning. So let's go a little step deeper, and let's write this equation down in terms of math, how we would typically see it. In a little more detail. I mean, it's the same exact thing, but we're just going to write it down in terms of math. So what you would have is IA, which is the line current, is equal to the square root of 3. So if I'm writing this for the A phase, the way I would write it is the phase current, which is going to be IAB. I'll show you on the drawing where that is in a second, with a phase angle of negative, positive 30 degrees. Again, you choose the sign appropriately. Now again, in some books or whatever, you might see this written as I phi, the phase current quantity, right? So what you're saying here is line current, square root of 3, phase current, and then you have your phase shift. Now, IAB, capital AB, that is the phase current. That's the current going through the phase, right? Line current is I little a big A. So you can see where everything comes from. Phase current, line current. That's the general form of the equation. Phase current, line current, and sometimes you'll see this written like this. I usually write the equations in terms of the A phase with actual subscripts, but some books will just have I phi because it's basically the phase current of whatever phase you're writing the equation for. So in this case, if you just write it for the A phase, it looks just like this. All right? And then, don't forget that, so you choose the sign based on positive or negative phase sequence, right? But don't forget, let's go ahead and flip around here, that you can go the other way. So I'm going to go and I could say go other way if needed. In other words, if you know the phase current, yes, you just stick it in here, multiply square root of 3 times the phase, and then you either add or subtract 30 degrees, and then you'll get the line current. Great. Now I can, just like I showed you a minute ago, you can go in the opposite way. Let's solve the equation for this, because some problems will require you to do that. So the way you do that is you say IAB is equal to, let's do it like this. This guy here, IAA over square root of 3. And you can tuck this down underneath it also. It'll be negative positive 30 degrees like this. But in reality, for a positive phase sequence, what's really going to happen is you're going to have IAB is equal to 1 over the square root of 3 IAA. And then if it's a positive phase sequence, you've chosen the negative sign here. So when you move it upstairs, he becomes positive 30 degrees. This is exactly the rule I taught you before. And if it's a negative phase sequence, then it's going to be exactly the same thing, but with the opposite sign. So you have IAB is 1 over square root of 3 IAA. And if it were a negative phase sequence, you would have chosen the bottom sign. When you move it upstairs, he's going to be a negative sign. Now, it's very easy to look at all these equations and get your head rattled and realize, well, there's so many of them, but there's really not. There's only one for the delta load anyway. You know that you don't convert between voltages in the delta load because the voltages are the same. So you just know that because you have this mental image of the drawing in your head. You don't memorize it, you just kind of know it. You might want to draw this on kind of on the side of your paper for every time you take an exam anyway, right? But then you also know that the currents must need to be converted between because they're different. The line current and the phase current are different. And then you remember the form of the equations are always the same. It's line current, square root of 3, phase current, phase shift. The only thing you have to remember is that it's flipped upside down from before. So this is the only equation you really have to remember. For any phase sequence, you've chosen the appropriate sign. So if for whatever reason you have to go backwards and find the other quantity, then you just divide by, which makes you pop it up and make it negative as a multiplication, and you've done the same thing here. And we're going to do a lot of problems to show this to you. Actually, this form of the equation is actually what you're going to use more often than not, where you're going the opposite direction. Here's why. These problems are going to be very similar to the other problems. The first thing we're going to do is write a single phase equivalent circuit. Why do we write single phase equivalent circuits as the first step so much? Because if we can do that, we can find the line current very easily. In other words, that was always step one of all those other problems. We found the line current. That's IAA. So we usually know the line current right out of the gate. If we're given a circuit, we're going to do some math and transform this to make it a single phase equivalent circuit, but we're able to find the line current very simply. We will be able to. Though this line current is going to go into here, and you're going to do this calculation to find the phase current. So usually, you know the line current first, then you find the phase current. It's not usual that you actually know the phase current first, and then sometimes I can construct a problem to do that, of course, but usually I'm telling you find the line current, then find the phase current. And then as with all of these other problems, once you know a phase current, then you find the other phases for the B phase and the C phase just by adding and subtracting 120 degrees, just as we've done before. So that is the roadmap here. Let me make sure I've said everything. We actually use this more, yeah, pretty much. Now what we're going to do is, I'm going to stop this lesson now. I think I've talked enough about it. I just wanted to show you the duality of these loads and how the equations look really similar. But the math, I was kind of sloppy in getting it all on the board. What we're going to do in the next section is I'm going to have them side by side just so you can see everything one more time. It'll be a short lesson to summarize it for you. And then in the third lesson, I'm going to derive this equation. We're going to derive this equation. The methodology to derive it is very similar to how we derive the other equation for the Y load. It's not difficult, but we're going to crank through it and just so you know where it comes from, because right now it looks like black magic. You might say, well, how was this the case? Well, we're going to show you how it's the case, and then we're going to crank through problems. And we're going to use it so many times that it's going to seem very simple to you. So follow me on to the next lesson, and we'll continue learning about delta loads and three-phase circuits.